All right, we are ready for section 15.6, and we're going to learn a new type of integral called a surface integral. So it's kind of cool, again, thinking about this idea of all the different types of integrals we've been doing, right? We started with single variable integrals, where we're integrating over an interval of a number line. We did double integrals, where we integrated over area of a plane. We did triple integrals, where we integrated over volume of a solid. We did line integrals, where we integrated over the arc length of a curve. Now what we're going to do is surface integrals. And the surface integrals are probably going to most closely relate back to that idea of line integrals. So we're going to see a nice connector there between the two. So a bunch of stuff are in here, just kind of the setup of the scenario. So basically S is a surface. Here I represented it as a function, so we've got Z is G of Y, XY. And then R is the domain we're looking at over, essentially. So R is that region of the XY plane that I get when I project that surface S down. We need G and its first partial derivatives, so G sub X and G sub Y, to be continuous on R. And then we need our function that we're going to integrate. So F is the function we're actually integrating. We need F to be continuous on the surface S. Then what we're doing is the surface integral of my function F over S. So we're integrating the function over the surface. This is the original setup we're going to have. We're going to have like a double integral over S of F ds, so over the surface S. And then the way we're actually going to compute this is we're going to convert it to a double integral over R. So this is going to be a dA integral, a classic double integral. What we're going to do on the inside is we're going to take f of x, y, z. We're going to replace, we'll keep the x and the y, but replace z with the function it is in terms of x and y. So we'll end up with just two variables. So we'll plug in g in for z. And then remember when we did line integrals, what we did was attached to the function, we then multiplied it by the arc length of the line or the curve that we were integrating over. When we do surface integrals, we're going to multiply by what we would do to take the surface area of the surface we're integrating over. So we're going to then multiply this by the square root of 1 plus, we need the squares of the partial derivatives of the surface. So we'll have g sub x squared plus g sub y squared, and then we're going to do this dA. So we'll either do dy dx or dx dy, depending on how we decide to set up the bounds for R. So notice again, we get this idea that similar with all the other examples of types of integrals we've done, if you integrate f, the function of 1, then you should get the type of integral that you're doing. So when we did like a double integral over area, when you integrated 1, you just got area between curves. When you did a triple integral, a volume integral, where your function was 1, you got the volume of the solid that you were integrating over. When we did a line integral, if f was 1, we got the arc length of the curve. Now, notice, if f is 1, then this is just going to be the surface area of the surface. So that's kind of a nice way to remember the formula here of what extra goes into that surface. So this is all how it gets set up if our surface S is defined as a function, so Z equals G of XY. But remember, we also can represent surfaces parametrically. So we could instead have represented it with, say, a vector valued function, or this could have been a set of parametric equations, either way. But if we do represent it with a vector valued function, the vector valued function, rather than R being a region of the XY plane, D is a region of the UV plane. So basically just what are the parameters defined on. And then what we're going to do is we're going to essentially do the same idea, right? We're going to get that this surface integral of f of x, y, z ds. We're going to switch this to a double integral. This time it's going to be over d. because it's going to be either a du dv integral or a dv du integral. So u and v are going to be our variables here. We're going to take f, and this time the two variables I want the function to be in terms of are u and v. So we're going to plug in the parameterizations x, y, and z in for the variables x, y, and z. So we're going to do f of x of uv, y of uv, and z of uv. So we're basically turning f into a function of u and v instead of x and y. And then remember, we want to multiply by what's going to give us the surface area. So when we had parametric defined surfaces, to get the surface area, we took the magnitude of the cross product of the partial derivatives. So the magnitude of r sub u crossed with r sub v. And then we take that integral dA, which again, like I said, will depend on how you decide to set it up. If you decide to do du dv or dv du. So remember, r sub u is the vector valued function of taking all the partial derivatives with respect to u. R sub v is the vector valued function where you take all the partial derivatives with respect to v. And then the cross product is that vector defined function. And then we're going to take the magnitude of it, which will turn it into a function of u and v, not a vector valued function anymore. So in either case, you're basically taking the function, turning it into a two variable function, either of x and y in this case, or I suppose it could be two other variables. If it was like x is a function of y and z, then you would end up being in terms of y and z. But basically reduce it down to two variables by just plugging in the function where it needs to go, and then multiply by the surface area formula. Over here, turn it into a function of the parameters by plugging in the components of the vector valued function, and then again multiply by the portion that gives you the surface area to do surface integrals. So what we'll do next is just try some examples of surface integrals.